Happy day, everyone. This is Orekoya Olusegun Physics Mathematics Fundamentals on YouTube. Today, we are taking a topic under vector, and that topic is on vector equation of a line in space. Vector equation of a line in space. That is a three-dimensional space, the real number system in three-dimensional way. Now, we want to consider the equation, the vector equation of a line. Consider this line P0, P1, lying on this particular plane. We want to find the equation of this particular line. Let's say the line passes through point P0 and P1, and there is an arbitrary point taken anywhere on this straight line. Now, we want to describe the location of point P0, P, and P1 using what is called the position vector of each of these points. So what I'm going to do now is to take a fixed point, 0, down here. This particular fixed point is a point that is not moving. So now, to locate this point P0, I will go through this particular direction, this particular sense. This is a sense. This is a sense of this line until I reach this particular point P0. Now, this is the position of point P0. The position simply means the location of point P0. So I'm going to denote the vector of this particular point with A. Like we did in my other video, I've described what vector is all about. Vector, as a reminder, is a quantity that has both magnitude and direction. This particular line with this sense of the arrow is a vector in the sense that it has a magnitude. The magnitude is the length of this line, that is OP0, and the direction is given by the sense. So now, this particular vector that locates this particular P0 is a position vector. I can equally, obtain the position vector of this arbitrary point P by tracing it along this line up to the point P0, up to the point P that I have here. Now, the sense of this P, as I'm tracing it, is in this way. That is from the fixed point down to point P0. Now, for me to locate point P1, I'm going to get its own position vector by tracing it down to this particular point P1. So this is the sense of this position vector. So the position vector of point P0 is A bar, and this is the vector. Now, for the point P0, let me take the position vector as this R bar. This is a vector describing this particular position vector. Another vector describing the position of point P1, let me take it as this particular vector B0. Now, for us to describe the equation of this straight line on this plane, I'm going to express the position vector of this arbitrary point P using the vector R. Now, the coordinates of point P0 is given as x0, y0, z0. That means the decomposition of the vector A into the x direction, the y direction, and the z direction is x0, y0, z0, and it's called the coordinate of vector A. Now, the coordinate for this particular vector R that is locating the arbitrary point P, the coordinate is s, y, z. That is the decomposition of this position vector R into x direction component, y direction component, and the z direction component in what is called 3D space system. The same thing with this particular position vector B. It's decomposed into x1 direction, y1 direction, and z1 direction. Take note of that. Now, for me to describe the vector equation of this straight line, I want to express the position vector R in terms of position vector A and B. This is how I'm going to do it. Now, considering me moving from this fixed point to this R, there are other ways that I can reach from point 0 to point P. Like, for instance, I can move along this line. If I don't want to move along this line, I can move along this line and still get to point P. So in a nutshell, when I move along this line now, I return with this position R. So I'll write it as R bar is equal to, instead of moving along this point, I would rather move like this. That is A bar plus, then I move like this. That is P naught P. This direction. I've reached this. What I have here is the vector equation of this straight line P naught P1 lying on this plane. Now, what do I do with a vector P naught P? Like this particular vector P naught P, it lies on this same straight line P naught P1. So that means vector P naught P can be obtained in terms of vector P naught P1 by a scaling factor. What do I mean by that is this. Now, vector P naught P, that means from moving from P naught to P, I can do the same movement in this manner, like this. A, then plus R, I can get to that point P naught. But if I do not want to do that, I can scale down the vector P naught P1. How do we get P naught P1 first? I have P naught P1 moving this way. So I can equally move like this. I'm moving against this sense of this arrow because the arrow is originally moving up. So if I'm moving against this sense, A will be negative. So it's going to be minus A naught. Then I move this way, then I move this way. So this is moving along the positive B. Let me explain again. When I want to move from P naught to P1, I move this way, then I move that way, I get to my P1. So moving along this way is negative movement because it's against this sense. Then moving along this way is positive movement. So I have it as a plus B bar. So I've already gotten my P naught P1 as a B minus A. I'm just rewriting this as it is now. Now, how do we get P naught P? I'm talking about from here to here. I'm going to scale down the P1 P naught P1. So that means this particular vector P naught P is a scalar multiplication of vector P naught P1 because the two vectors are parallel. So I'll write it like bar B minus A. So I've gotten an expression for P naught P. That means from here to here, I haven't gotten the expression from P naught P1. So I'm going to have R now is equal to A plus, I'll put this one here now, alpha B minus A bar. Now, each of these vectors that I have here, I can write each of these components, each of these position vector in terms of their components. The component of this vector R is given as X, Y, Z. So I'll write it as a column vector, X, Y, Z. Then is equal to the component of vector A in column vector form is X naught, Y naught, Z naught for this A. So I put this there, X naught, Y naught, and Z naught. Then plus this scaling factor times the component of this vector B in term the component of this vector B is S1, Y1, Z1, X1, Y1, Z1 minus the component of vector A, which is this. So I write X naught, Y naught, and Z naught. So that is what I have here now is the equation of this line P naught P1. Equation of line P naught P1. That is the equation, the vector equation of this particular straight line. This is the formula. Now, let's do a little exercise. And this exercise we want to do now, the question is given like this. The question states that determine the vector equation of a line in a real number system if it passes through the point A given as 2 minus 1, 5, and point B given as 8 minus 3, 7, and that our results should be expressed in parametric form and in symmetric form. How do we do that? That's what we want to do now. Now, like I did the other time, I already stated my vector equation to be this. So I will write my vector equation, the vector equation of that straight line, as x, y, z will be equal to x naught, y naught, and z naught, then plus the scaling factor of the difference between this vector for the point P1, that is S1, Y1, and Z1, then minus the vector X0, Y0, and Z0. Now, in the problem that we have above, point A is given as 2 minus 1 and 5, and that component is actually X0, Y0, Z0. The second one, point B, the vector for the point B given in the question, which is 8 minus 3, 7. I'll write it as 8 minus 3, 7. That is the vector for the point B, which is presented in this equation as S1, Y1, and Z1, as we have here. Now, I'm going to substitute what I have here in this equation now. So my vector equation now can be stated as x column vector x, y, z, then is equal to 2 minus 1, 5, plus the scaling factor of the difference between these two vectors, that is 8 minus 3, 7, minus 2 minus 1 and 5. So what I have here is the substitution of this vector equation that we have up. Now, so let's work this one out now. We have x, y, z is equal to 2 minus 1, 5, then plus the scaling factor. 8 take away 2, give us 6. Minus 3 minus 1. Minus times minus give us plus. Minus 3 plus 1 will give us minus 2. Then 7 minus 5 will give us 2. We can factorize 2 out here. So I can still rewrite my vector equation in this form. That's 2 minus 1, 5. Then plus, if I factorize 2 out of this place, I'll use the 2 to multiply the scaling factor. So I'm left with 3 minus 1 and 1. This scaling factor is a constant. I can play with constant k. These two. So I can play with constant k. So my vector equation now will be x, y, z is equal to 2 minus 1, 5. Then plus k bracket 3 minus 1, 1. And this expression that I have here can be written in a rectangular form as 2i minus j, then plus 5, then plus 3ki minus kj plus 1 times k, that's k, plus kz. So what I have here is the rectangular form. But what I have here is a vector, column vector form. So the question we have here is that we should express our equation in parametric form and in symmetric form. So in parametric form, x will be equal to 2 plus 3k. So x now will be equal to 2 plus 3k. I'm talking about this x. the one up will be equal to one another. Everything up there will be equal to one another. So whatever I have here will be equal to everything there. So then the next one, y will be equal to the one in the middle. So my y now will be equal to minus 1, then minus times k, that's minus k. Then z will be equal to, correspond to the component down. That z is equal to 5 plus k times 1, that is k. So this expression that I have down here is called the parametric form. Parametric. So this is our parametric form. Now, to express what I have here in symmetric form is to make k, this particular scalar, the subject of formula in each case, in each of the cases. So for the equation 1, I will take every other thing here, leaving k behind. So taking 2 to the other side will be minus. So it's going to be x minus 2. Then I'm left with 3k. Then to leave k alone, divide by 3. So I'm left with x minus 2 divided by 3. This 3 cancel this 3. So I have a k there. This is the first symmetric. Then for the y is equal to minus 1 minus k, I can carry this minus k to this other side to make it positive, and carry y to the other side, making negative. So k in this case will now be minus 1 minus y. This is the second symmetric form. Then for the third one, that's dz, I still make k solve the formula. So we carry 5 to the other side. I'm going to have z minus 5 is equal to k. This is the third symmetric form. Since everything is equal to k, I can equate everything together. So that means this implies that x minus 2 divided by 3 will be equal to minus 1 minus y, then will be equal to z minus 5, everything equal to k. So this expression I have here now is known as this symmetric form. It's known as a symmetric form. So this is the end of the proof of the formula for the equation, the vector equation of a straight line, and a related exercise concerning this particular topic. Once again, this is Orekoya Olusegun Physics Mathematics Fundamental on YouTube. Please do not forget to subscribe, share, click on notification button, and also make sure that you are in tune with my subsequent video. Thank you so much. Have a nice day. Bye.